Hello everyone, hope you guys are doing really good. So today we're going to get into the last phase of homogeneous transformations, and in that we plan to discuss axis angle representation, which is one form of the parameterization of rotations that we started last time. And once done, we will sum it up all and we will discuss that what is the final form of homogeneous transformations. And that will prepare us for the subsequent discussion on forward kinematics. So let's start the discussion. Last time we said that if a rotation matrix is available to you, it is going to have a 3 by 3 structure, which would mean that you have 9 unknown parameters requiring 9 equations. So how to solve it? We said the starting point may be like to observe the properties of the rotation matrix and observe how those properties can be manipulated. So we did that. And in that, the very first property to be manipulated was that of special orthogonal matrices, where we say that columns and rows are going to have unit magnitude. And when we tried that, that was this expression that gave us 3 equations. So these 3 equations that we have on our screen are a result of manipulating this property of the special orthogonal matrices. So we have got by the end of this exercise 3 equations, but still 6 remaining equations are to be found. And then we said that why not use another property of the special orthogonal matrices to help us out. And that was when we said that the columns and rows are going to be mutually orthogonal. When we exhaust this property, we observe that this is going to be the expression, and that is going to give us 3 more equations out of the remaining 6 equations. So that was done, but still there are 3 more equations to be found out. And that is when we said that why not use Euler angles in order to decompose a rotation into 3 constituent rotations according to the Euler notations. So that is when we said that you are going to have the rotation matrix of the first frame with respect to 0th frame to be decomposed into the first rotation being rotation about z-axis by phi, then the second rotation which is about y-axis by theta, and then the third rotation which is once again about the current z-axis by psi radians. So when we do that, we are going to have 3 more parameters, phi, theta, and psi to be available in the notations, which we can try to find equations for. And that is exactly what we did. And when we did that, we found this big matrix, which we manipulated to find an expression for theta, an expression for phi, and another expression for psi, which are the 3 more equations required in order to solve the full 3 by 3 rotation matrix. And now we can raise this question over here that what if we are not interested in principal rotations about x-axis, y-axis, or z-axis, for which we have already the expressions? What if we are interested in rotation about an arbitrary axis in space, and we wish to find an expression for that? Probably that would be more general purpose expression that we can use later on. So this is the quest today. We call this arrangement to be axis angle representation. And in that, there is a unit vector k about which the rotation is happening. You can see this vector right over here. And the rotation about this axis is theta rotation that you can also observe. And you can also observe that this rotation is not about x-axis or y-axis or z-axis, which are the principal rotations. So we are trying to find out one general purpose expression which defines any rotation about an arbitrary axis k. And this is the quest over here. But the problem that we're facing over here is that we only know the rotations about x, y, and z axes, which we have already derived earlier. So is there any way we can find an expression for this rotation about an arbitrary axis k using the principal rotations? So there can be multiple ways to derive such kind of expression, but we will do one graphical approach initially. For this purpose, what we're going to do is to take this vector k and rotate it minus alpha by the fixed z-axis. So that would be like the first rotation is rotation about z by minus alpha. So once done, you're going to expect this vector k to be oriented in xz plane, and that would look somewhat of this shape. Now once you have this vector k in the xz plane, then you can go minus beta about the fixed y-axis, and that would be the second rotation about y, fixed y, by minus beta radians. And if you do that, once done, you're going to expect this arbitrary vector k to be perfectly aligned with the z0 axis. And now you can have the rotation about the z-axis by value theta, and that can be written like this, rz by theta. And once you're going to execute that rotation, so that would be the rotation about that vector k, but then because you have gone minus beta and minus alpha about y and z respectively, you need to get back. You need to do the compensation for that, and that would be rotation about y by beta and then rotation about z by alpha to recompensate the first two rotations that you executed to align yourself about the z-axis. So when you do that, these are going to be the 5 rotations: 1, 2, 3, 4, and 5. These are the 5 constituent rotations that you have used in order to execute the rotation about the arbitrary vector k by value theta. But in this particular scenario, you can also observe that this arrangement was corresponding to the fixed frame defined with x0, y0, and z0. So everything that is listed over here is with respect to the fixed frame. So that's why you are going to, in terms of composition of rotation, you are going to change the order of multiplication. So if this was the route taken like 1 to 2 and 3, 4, and 5, in terms of multiplication, you're going to start from here and you can go backwards to execute the expression. So that would be the rotation about arbitrary vector k by value theta is going to be equal to, you're going to write down rz alpha first, then ry beta, then rz theta, then ry minus beta, and then rz minus alpha. So these are going to be the principal rotations used to derive an expression for rk theta. So this expression is a result of multiplying these 5 matrices together, but because it is with respect to fixed frame of reference, so that's why the order of multiplication is going to be reversed. So that is how you derive rk theta. But there is a little problem in this expression for rk theta. I've written down this expression in a neat form now, but you can observe that it requires alpha and beta in it, which obviously are the two angles which are arbitrarily defined, and we may not have the knowledge of these. So we need to find some other way to replace alphas and betas in this whole expression. So what I would do in that particular scenario, I'll start from once again defining the vector k, which is obviously a unit vector, and this is going to have three components in it: x, y, and z components. Obviously it needs to be transposed. So with this vector k that is unit magnitude vector, this would say that this vector, when taken the magnitude, is going to be equal to 1, which means that you have kx squared plus ky squared plus kz squared taken the square root of is going to be equal to 1. Now on the diagram, on the figure that you can observe over here, you have this vector k defined over here. So I'll try to find all these components which are shown in dashed lines so that I can replace the alphas and betas in this whole big expression. So let's try to find out those. So if you have kx available over here as one component of the right angle triangle at the base plane x and y, so this is going to be ky, and for that reason you have this dashed line to be kx squared plus ky squared square root. Now with this realization that you have one component placed already on the diagram, you can find out the other expressions. So this dashed line over here, which is along the z-axis, is obviously the z component. So I can readily see that this is kz, which obviously is also observed over here. Now, when you take the projection of vector k onto the axis z0, you can have the expression for beta as well. So in that particular scenario, kz can be used to find the expression for cos of beta. So I can say that cos of beta is equal to kz. Why so? Because I can readily see that this is kz, and if I take the projection of arbitrary vector k onto the z-axis, obviously that would be cos of beta, and that's why I've written down this expression, cos of beta, to be equal to kz. Now what about the sine of beta? Obviously that would be this line segment, but this line segment is already taken care of when I wrote down this expression kx squared plus ky squared, the square root of. So I can obviously see that this line and this line are parallel and equal, so that's why I can write down the expression for sine of beta. So that is going to be equal to kx squared plus ky squared whole taken the square root of. And obviously this is with the realization that you have the magnitude of k to be equal to 1. That's why the direction cosines are accounted for in this particular scenario. Now what about the alpha? So I can think about the cos of alpha on similar grounds. What is going to be the expression for that? So you can observe in this scenario that cos of alpha for this triangle, right angle triangle, can be very easily found out, and that would be that you have this to be equal to base over hypotenuse, and base is obviously kx, whereas the hypotenuse is already computed, kx squared plus ky squared. So this is going to be the expression for cos of alpha, and similarly you can write an expression for sine of alpha as well, which is going to be perpendicular over the hypotenuse, and perpendicular obviously is ky over the same denominator, kx squared plus ky squared. So now in this particular case, you can see that you have an expression, a couple of expressions for cos of beta, and a couple of obviously for beta, and a couple of expressions for alphas, which you can use in the big expression that you have derived over here in order to find an expression free from alpha and beta in them. So after a bit of manipulation, you are going to find out that this expression is going to be transformed into this big matrix. And this is defining the rotation about an arbitrary vector k by theta. And in this particular matrix, you can observe that there is no instance of alpha, there is no instance of beta in it. Only that is being used over here is kx, ky, and kz, and the theta rotation in it. So this is a general purpose rotation matrix that we are going to use eventually to find out any rotation about an arbitrary axis. The only little thing that you must observe is that v theta in this expression is nothing complex. It is called verse of theta, which is just like 1 minus cos of theta. So we're using this to write the expression in a nicer form. Now, since we have derived an expression for rotation about any arbitrary axis, we would love to use it to our benefit. I'll make use of two properties of this rotation matrix. The very first one is this, that you have theta to be equal to cos inverse of trace of rotation matrix minus 1 whole over 2. Now this is going to give me the angular displacement about the arbitrary axis k. The trace of a rotation matrix, obviously, I must make you recall that this is going to be just like the addition of the diagonal terms. So this term added with this, added with this. So we can quickly do that and see whether it is truly equal to that expression or not. So let's try to see what is that. So that would be equal to cos inverse of R11, which is kx squared v of theta plus cos of theta plus ky squared v of theta plus cos of theta plus kz squared v of theta plus cos of theta. This is the trace minus 1 whole over 2. So I can write that over here. Now once you have got that, I can expand it further. So this is going to be cos inverse of, I can take v of theta common from here. So the remaining expression is going to be kx squared plus ky squared plus kz squared plus cos of theta plus cos of theta plus cos of theta, which is going to be 3 cos of theta minus 1 into 1 by 2. Then you can further manipulate it. This is going to be cos inverse of, now since you know that the magnitude of k vector was equal to 1, and that was actually equal to kx squared plus ky squared plus kz squared, which you're using over here as well. So that would be equal to, for that matter, v of theta into 1 plus 3 cos of theta minus 1 and then 1 by 2. So this is going to be equal to cos of theta, cos inverse, sorry, and then you have v of theta, which is actually 1 minus cos of theta plus 3 cos of theta minus 1, and then you have 1 by 2. Obviously that can be further simplified. So this 1 can be cancelled with this -1, and then you have 1 cos of theta with a minus sign taken away from this 3 cos of theta. So this is going to be 2 cos of theta for that matter. So this is going to be 2 cos of theta. Then you can take the 2 inside. So this 2 can be cancelled with this. And that would mean that you have cos inverse of cos of theta, which actually is equal to theta. So this is proved. Now, the basic concept is not to have this proof presented to you, but to give you this property. This property which says that you can find out the theta about the arbitrary axis k by exploiting this expression. So you can have any rotation matrix R, and then you can find out what is going to be the angular displacement about an axis. So this is what we're going to use in one of the examples later, but this is going to be one very good property to give you the equivalent angle for any rotation matrix R. The second expression that I would like to present over here is the expression for the vector k itself, obviously using the rotation matrix that we have derived already, which is this. Now in this particular scenario, you can see that the vector k is going to have 3 components. The first component is kx, which corresponds to this location, and over here you'll find expression for ky, and over here you have expression for kz. So this arbitrary axis k is defined with this expression, and this is also going to be very useful for us to define the equivalent axis about any composition of rotations as well. And I'm emphasizing composition of rotations over here because in case of robotic manipulators where you have multiple joints combined together, obviously you are going to have multiple rotations merged together. So you would love to have some sort of formulation which allows you to compose rotations together. So in this continuation, this is going to become an important expression. So let's try to find out whether I can recreate kx using this expression that I've shown you just now. So kx in that case is going to be equal to 1 over 2 sine of theta, and then you have r32 minus r23. Now that would be, in that particular scenario, r32 is the element in the third row and second column, which is this, and r23, which is going to be in the second row and third column. This element is this. So I'm going to make use of these two elements in order to come up with the expression for kx, and that is going to be 1 over 2 sine of theta, and then you have ky, kz, v of theta, plus kx sine of theta, and then you have minus ky, kz, v of theta, minus plus kx sine of theta. Now obviously you can see that this can be cancelled with this because of the opposite signs, and that would give us an expression like this, 1 over 2 sine of theta, and then you have inside 2 kx sine of theta. And obviously 2 sine of theta can be cancelling this 2 and this sine of theta, and obviously for that matter this is equal to kx. So that's why this is proved as well. But now once again I would emphasize this point that this proof is not important. The important realization is over here to find this expression for the arbitrary axis k. And when combined with the earlier expression for the equivalent angle, you can say that given any rotation, you can find out using these two expressions that what is the equivalent angular displacement or rotation about this vector k, and that would give you the combined effect of any composition of rotation in your system. Whether it is for robotics or for any other application, you can use this very generic, very powerful set of expressions. Let's do one example to illustrate this whole process. Now, in this particular case, you have a rotation matrix available with you, but now you can see that this rotation matrix is a result of having three rotations in it. The very first rotation is of 90 degrees about z0 axis, which is followed by another rotation of 30 degrees about y0 axis. But at this particular stage, you can emphasize that because z0 and y0 are with subscript 0, so it would mean that you have a fixed frame about which these rotations are happening. So you have in back of your mind this observation that you have to reverse the order of multiplication. Now, after these two rotations, you have another rotation of 60 degrees about the fixed x0 axis. So with this observation that you have fixed frame of reference arrangement, you would say that you are going to find out the overall rotation, which is going to be all these three rotations but in reversed order. So you have rotation about x first by 60 degrees, then you have rotation about y by 30 degrees, and then you have rotation about z by 90 degrees. So when you combine and multiply these principal rotations together, you are going to find a matrix which is this. Now this matrix is needed to be manipulated further in order to find out what is going to be the equivalent angle about an arbitrary axis. So this is the quest over here. The idea is not to give you the overall rotation, but the two properties that we have derived earlier corresponding to the axis angle representation. The very first one was corresponding to the angle. So the equivalent angle was equal to cos inverse of trace of any rotation matrix R, and in this case you have a composition of rotation minus 1 whole over 2. Now in this particular case, I can readily find out the trace cos inverse of the elements on the diagonal. So this is going to be 0 minus 3 under root by 4 plus 3 under root by 4. Obviously these two are going to cancel each other out. Minus 1 whole over 2. So this is obviously going to be cos inverse of minus 1 by 2. And that is not very complex. This is actually equal to 120 degrees. So what does that mean? It means that when you have all these three rotations multiplied together, this is going to be equivalent to having 120 degrees of rotation about an axis, which I'm not very much sure of it. Let's find that one out using the other expression that we derived earlier. And that was corresponding to vector k, which was 1 over 2 sine of theta, if I recall correctly. And that was something like r32 minus r23, and then you had the other element like r13 minus r31, and the last one I suppose was r21 minus r12. Now if you have that as the expression for arbitrary vector k, you can manipulate the expression that you have derived for the rotation matrix R, this expression, to find out all these components over here. So this would mean that kx in that scenario is going to be equal to 1 over 2 sine of now 120 degrees Then you have R32 minus R23, which you can obviously write that one down. So this is equal to 1 over 2. Sine of 120 is actually equal to sine of 60, and that is, if I recall correctly, this is 3 under root by 2. So you can cancel these two out. So this is going to be 1 over 3 under root. So R32 is this term over here, and R23 is this term over here. So you have 1 over 4 minus plus 3 by 4 to be there, and that is when manipulated, it is going to be 1 over 3 under root, and then you have 4 over 4, which is equal to 1, and that obviously is equal to 1 over 3 under root. So this is kx, and similarly you can find out ky, which if you do, you can do that exercise on your own. This is going to be 1 over 2 under root 3 minus 1 by 2, and kz is equal to the conjugate of this, which is equal to 1 over 2 3 under root plus 1 over 2. So you have these three, kx, ky, and kz, to be the three coordinates of arbitrary vector k. Now it would mean in that sense that when you have these three rotations, in your case about 90 degrees about z-axis, and then 30 degrees about y-axis, and 60 degrees about x0 axis, that would be equal to having 120 degrees rotation about an arbitrary vector k having these three components, 1 by 3, then you have this element, and then you have this element. So this is the vector k about which you have 120 degrees of equivalent rotation as a result of that. So this is going to be giving you a good synthesis of having a multi-body rotations kind of given into you or presented to you in an equivalent fashion. So that's why this whole process was executed with much more detail over here. Now at this stage we can sum up all the discussion. The homogeneous transformation is defined for any body which is rotating and translating. So you can say that if a body is rotating as well as translating, the homogeneous transformation is going to give us a matrix valued expression for it, which contains a vector for the translation over here, which is d, for example, and which gives us the rotation matrix, which is a 3 by 3 matrix over here. And then you have zeros in the last row except the last element. So this body, which is having a rotation defined with a matrix R, and the translation which is defined with D, can be defined using homogeneous transformations. And obviously you can also recall that we said that the position of point P in the zeroth frame or not moving frame was defined to be having a rotation of the first frame with respect to zeroth frame multiplied with the location of the same point P in the body attached frame added with the translation of the frame itself, which is D10. So this was the expression that we have kind of used over here in a matrix arrangement. But in a generic form, homogeneous transformation takes a bit of modified shape as well. Although we're not using it in this form, but let's see the structure over here. Rotation matrix we have seen already. This remains as we have defined already. The translation vector remains over here as well. But this last row is a bit modified in a generic homogeneous transformations. The last row, the first three elements are going to account for perspective and that may be used in the computer vision course that you are going to study later on. And then you can have the scaling factor added in the transformation as well in the last element as well. So this is a more generic form, but because in case of robotic manipulators we are considering the rigid body motion, so that's why we are only concerned about the rotation and the translation. So that's why the last row becomes 0, 0, 0, 1. But for multi-body systems such as robotic manipulators, you have multiple such movements in a system. So let's try to find out how we're going to proceed with that. So if you have the first motion defined in this fashion, that you have position of the point P attached to a rigid body in the not moving frame defined like R10 times P1 plus D10, as we have done already. And then you have another motion. And that would be like P1 to be equal to R21 times P2 plus D21. Now, in this particular case, you can readily observe that P1 is appearing over here, which you can replace with this whole expression over here. So that would mean, using the consistent color, that would mean that P0 is equal to R10, and then you can plug in this whole expression, which is R21 times P in the second frame plus D21 added with D10. Now this would mean that the location of the point P in the not moving frame or fixed frame is equal to R10 times R21. And obviously you can recall that that was equal to rotation of the second frame with respect to not moving frame in the composition of rotation discussion that we have already had, times P2 plus R10 times D21 plus D10. Now in this particular case, if you have, for example, some more movements added to it, such as would be the case in N-link robotic manipulators, then obviously it will be more complex expression. Now at this particular stage, I would raise this question over here, that can we use homogeneous transformations, the matrices of homogeneous transformations, to help us out? And obviously we can use that. So that's what we will try over here. So let's have a homogeneous transformation of the first motion, which is going to be R10, D10, 0 and 1, multiplied with the rotation, the second motion, which is R21, D21, 0s and 1. When you multiply these two together, you are going to have another matrix, which is the beauty of homogeneous transformations. Let's try to find that one out. So first column would yield R10 times R21 over here, and then the first row second column is going to give us R10 multiplied with D21 added with D10. And then you have second row, which is going to give us 0, and the third in the second row, the second element, which is obviously going to be equal to 1. Now you can readily observe in this particular case that this retains the structure. Homogeneous transformation is going to have the vector of all zeros over here, 0, 0, 0 over here. It is going to have 1 over here, which is consistent with the earlier transformations that you have observed. And you can see that over here in this 3 by 3 space, you are going to have a rotation matrix, which is after composition of multiple rotations placed over here. And then you have a vector added over here. And on top of that, you can observe that this is the same thing appearing over here. And if I use a different color, this is the same expression appearing over here. So homogeneous transformation is going to make your life easy by giving you the matrices multiplied together, retaining all those properties of the special orthogonal rotation matrices, and it is going to complete the job in much more easy fashion and in much more quicker fashion as well. So that's why homogeneous transformations are going to be used for robotic manipulators where you have multiple bodies connected together. In order to further substantiate our claim that homogeneous transformations are going to make your life easy, let's see how the inverse is taken. So if homogeneous transformation is defined like having a rotation and translation vector 0 and 1 over here, let's take the inverse of it. So this is going to be equal to when you take the adjoint and multiply with the determinant. So in this particular case, the adjoint is when you replace the position over here and change the signs for the diagonal elements. So we're going to do that. So there's going to be 1 and r over here minus d and 0 over here, divided by the determinant of h, which is r minus d into 0. So this is going to be r, obviously. So when you have divided by r, it means that you have r inverse. So I can do that, which is going to be 1 over r. Then you have minus d over r. You have 0 and you have r over r. Actually, r is a matrix which is in the denominator, which means that you have to take the inverse of it. But when you take the inverse of a rotation matrix, you can recall that that was very easily done by taking the transpose of the rotation matrix. So this is going to be, if I take one step more, like r inverse, then you have minus r inverse d, then you have 0, then you have obviously identity matrix over here, and that is going to give you equal to r transpose minus r transposed d, then you have 0 and you have 1 over here. So this is obviously, you can see that this is much more easily computable in a sense that all you have to do is to take the transpose of a rotation matrix, and then for this vector you have to multiply the transpose with the translation vector d, and that would be it. That would make you calculate the inverse of a 4x4 matrix, which otherwise would be very difficult to manage. And finally, we can define the basic homogeneous transformations. Like corresponding to x-axis, this is going to be your translation transformation and rotation transformation. And you can see very quickly that translation is happening along x direction by a units. So in this particular case, you have an identity matrix in place of the rotation matrix. So it means that there is no rotation happening. And corresponding to the vector of translation, you can see that all are 0 except the first element corresponding to x. Similarly, for the rotation happening about x-axis by an angle alpha, you can see that this rotation matrix is what you have seen already in case of rotation matrices. We have discussed the rotation about x already, so this takes the same shape that we have seen already. And obviously there is no translation, so that's why this vector over here becomes 0, 0, 0. And similarly, you can have a basic transformation for the y-axis as well, which are over here, and as well as for the z-axis. So these are the 6 basic transformations generally used for the robotic manipulators, and we will see those later on in case of your forward kinematics as well. Now in the very last stage, let's see one quick example. Over here you have homogeneous transformation matrix H to be constructed when you know that you are going to have initially a rotation of alpha degrees about the current x-axis. So this is first transformation. The second transformation is a translation of B units along the current x-axis. So this is again x-axis, but it is translation that we are trying to handle. And then you have followed by a translation of D units along the current z-axis. So that's the third transformation that we're going to use, followed by a rotation of theta degrees about the current z-axis. So the last two transformations are once again about the z-axis. So if you have that arrangement and you know that you have the current frame of reference arrangement, all you have to do is to multiply these four basic transformations in the same order. And when you do that, this is going to be your answer. And this final transformation over here is indicating that you have all these two translations and two rotations multiplied together, giving you this matrix. And at this particular stage, I can safely say that we have covered all the requisite detail that we wanted to cover in homogeneous transformations. And now we are well equipped to handle any kinematics related task for robotic manipulators. So that's why we're going to stop over here. Next time, we are going to handle forward kinematics for robotic manipulators. So until then, bye-bye.